First of all, let me thank for this great honor to be the first speaker here for the invitation to this conference. So the topic is a kind of advertisement of an hopefully emerging new subject, combinatorial topological dynamics. The word combinatorial here should be understood as based on mathematics referring to finite sets. Probably most of you are aware, or maybe not, that algebraic topology at the very beginnings used to be called combinatorial topology, because at least at that time, to make these algebraic computations in topology, you needed a bridge, a kind of finite structure, for instance, a simple complex. Later, some more sophisticated cellular complexes. And out of that, you could build all the algebra and then use it to get useful conclusions in topology. So in similar spirit, I want to speak today about combinatorial approach to dynamics. But maybe I'd like to begin with a quick recall of topological dynamics and, of course, a very personal view of this broad topic. So, is it working? Slide changer. Thank you. In terms of applications, of course, when you speak about dynamics, you think about an autonomous differential equation, or you just take a topological space and a map, you keep iterating it. So you have these two versions of a dynamical system with continuous time and discrete time. But if you want to make applications, you assume that explicit formulas for this vector field V or for the map F are known. You're interested in solutions. But mathematicians quickly realized that even if you know explicit formulas for V and F, it's not so easy to get explicit formulas for solutions. So they started to study the solutions without knowing the formulas, and this required this concept, the formalization of a dynamical system. So here is the definitions we usually learn when we start learning the subject of dynamical systems. Here, let me only emphasize that this time t is just considered to be reals or integers, but today I mostly concentrate on a strange situation, because I'll concentrate on a combinatorial analog of a dynamical system with continuous time, but nevertheless everything would be finite. So it looks a little bit strange at this stage. I hope I'll be able to explain it. Let me recall that once you're given such an abstract dynamical system, then you can speak about the solution through X. It's just the map which sends T to F phi of XD. And the trajectory is just the image of this map. And the goal is to study the long-time behavior of solutions. So you want to predict the future, what eventually will happen with the dynamical system. And in terms of topological tools in dynamics, so as I said, this is a very personal view. I had never chance to meet Professor Wajewski, a kind of my mathematical grandfather, although theoretically I had a chance, because I started mathematical studies when he passed away. So there was a chance, but I never met him personally. So he was among the first who realized that Poincaré, who invented topology and algebraic topology, invented it as a tool to study dynamical systems. But then it was quickly forgotten, because the subject itself was so interesting that mathematicians started studying topology itself. And it took like 40 or 50 years to recall that these tools were invented to use in dynamics, and Professor Warzewski was among the first to really use it again. And modern reformulation of his famous retract theorem is based on the concept of isolating block. Warzewski formulated it differently, but this is equivalent. Namely, you pick up a compact set in your topological space X, and you are interested whether, for instance, there is a solution which stays forever in that set, a bounded solution by this region. But without formulas, it's a difficult task, but it turns out that if you're at least able to understand what's going on the boundary of this region, in particular, if you're able to distinguish between points where trajectories go out, solutions go out, and solutions go in, and if this set is compact, like on the left side, because on the right side, it's not compact. This point is no longer an exit set, but arbitrarily close to points in exit set. So this compactness actually may be reformulated as the situation where these internal tangencies are not allowed. This is part actually of the proof of the Warzewski theorem. So the theorem itself, in this more computational language, says that if N is an isolating block, so these internal tangencies are excluded, or the exit set is closed, then and the relative homology of the whole compact N relative to this red set of exit points is non-trivial, then there must be a point inside where the solution stays there forever. Later, Charles Conway, American mathematician, took the Warzewski's ideas and turned it into a kind of index. So a feature you can compute, it has several nice properties which are also helpful in computing it. And in particular, he introduced a slightly more general concept of isolating neighborhood. So actually, he allowed this internal tangency, but requested that such an internal tangency is not related to a trajectory which actually stays forever inside. So he said that N is an isolating neighborhood. If you take the set of all points whose whole trajectory since inside, in this case, in this picture, this, then it cannot touch the boundary as here. So here it is not much a boundary. So despite the internal tangency, this is an isolating neighborhood. And then invariant sets, which allow such an isolated neighborhood, we call them isolated invariant sets. And this is the situation where we introduced this index based on the Warzewski's ideas. This required two theorems that for every isolating neighborhood of such an isolated invariant set, there exists an isolating block in the sense of Warzewski inside between. And moreover, and most importantly, if you have two such blocks, and in fact there are many, then the relative homology is the same. So this thing used by Warzewski to find the existence of a stationary solution. And this is now called the homological Conley index. Of course, there is the original version of Warzewski was not based on homology, but more general concept of homotopy, and also Conley index was based on homotopy, but in practical terms, if you want to compute something, particularly compute algorithmically, then typically you use homology. In fact, here I'll just show the Conley index in examples in the form of Conley polynomial. You just take all the Betti numbers of this relative homology, you make its formal power series. So that this is the minimum information you get from the Conley index, these Betti numbers. So here are a few examples of the computations of the Conley index. Maybe I'll not go into details. Maybe just one example. For instance, let's take this N, which takes the form of a disk. And here, of course, I've visualize what you may expect inside, and actually a repelling periodic trajectory, but actually what really matters is only what happens on the boundary. So if the boundary, as in this case, is exit set everywhere, then the relative homology is the homology will collapse. So one way of computing relative homology is to collapse the exit set to a point, and then you have two sphere with a one-dimensional handle attached to it. So this is the Conley polynomial of this example. Again, whenever the Conley index is different from zero, so the homology is also different from zero, there must be something inside. In this case, this might be this periodic trajectory, repelling periodic trajectory. It may be something more complicated, but for sure something must stay inside. So the only situation where there is nothing inside is where the Conley index is zero, and here it's just from the proof of the Wajewski theorem, you can find a deformation retraction going along the trajectories, so you can push everything to the exit set, and this causes the relative homology is zero in that case. Okay, and so this was just an example of the topological invariant. There are many others used in topological dynamics, like fixed point index, topological degree, connection matrices, which is a sophisticated algebraic concept built on top of the Conley theory. But they were used, and the Conley theory is like the late 70s of the 20th century. Until the end of the 20th century, you should see many publications using these tools to prove the existence of various types of bounded solutions, so not just bounded, but stationary, periodic, homoclinic, heteroclinic connections, or even chaotic and invariant sets. But then the paper started to die out because, and that was interesting, because the reason was not that all the situations where you could use that were done. It just was just a difficulty anyway in computing the index. So you could expect numerically in many situations that you should have an isolating neighborhood, but analytically construct, because the main tool to find the index was to construct an isolating block. And analytically construct, you knew from the theorem that it is somewhere there. Actually, there are many. But it's one story to know it is there, another story is to construct. So what people did, since they referred to what people do in differential equations anyway, since we don't have the formulas, closed formulas for the solutions, we just take a computer and make a numerical simulation. So the discretization of the differential equation actually turned out to be useful to build so-called computer-assisted proofs, which let you find the Conley index with the help of the computer. So this, what was difficult manually, analytically construct an isolating block, computer could construct for you this isolating block, and from that find the index, and still it turned out that you can make use of it. So already here in this proofs, you see the taste of combinatorial dynamics. I do not have time to explain the whole idea of these computer-assisted proofs, but roughly speaking, you divide your space into small pieces, for instance, squares, cubes, and then you try to get rigorous estimates of the image out under the map. So the time one map in case of the differential equations, or if you use it for dynamical system with discrete time, just f. So if you have a formula for this vector field or for f and a numerical method, you could get out of that the rigorous estimate of the image of the set. Of course, the estimate of about the whole space is also the estimate. So the question of success was whether this estimate was good enough to guarantee that using these estimates you can start an algorithm produce and guarantee for you that you found this isolating block. But the main reason I showed this slide is that, in fact, this way, what you construct is a directed graph. You have this finite collection of your cells where you divided your space, and then the image under this rigorous computation is covered again by the pieces of your division of space, and then you construct a directed graph which sends each square to the collection of squares which cover the image. So here you have a directed graph taking the form of a kind of combinatorial dynamical system. Actually, such a directed graph may be obtained not only when you do computer-assisted proofs, but also when you try to reconstruct dynamics from samples. So you have a time series. The only way you observe the dynamical system is via a time series. And then again, when you divide the space into pieces, you see that at the moment something is in this square, and next moment it's a different square. And then you get again a directed graph. This multi-validness here matters because you may have points which fall into this square, but for different points in this square, their images may be in different squares. So you will see here this multi-validness, which is also important in the rest of my talk. So the combinatorial dynamics may be viewed as the study of directed graphs. But of course, this way, it's only hidden somewhere that you do something with the directed graphs, but everything interesting happens on the side of classical dynamics and classical topology. So these are just an example of a few examples of situations you can just get instead of a computer-assisted proof, you just get a sample dynamical system. Maybe only one comment. There are two sorts of them. They take the form either just of a time series, like the top line, or they can take also the form of a cloud of vectors. So you have a cloud of points, and at every point you have a direction where you expect at this point to move on. So this is like the combinatorial representation of something where the time is expected to be continuous. This vector tells you how to move in the space, whereas in the top line, it's most likely something with discrete time. You just have this jumps from point to point. We'll go back to that later. So the sample dynamical system reveals itself only through a finite data set coming from observation, experiments, or evaluations. And typically, where you are in trouble with such sample dynamical system is that this analytic formula which governs the system is known only roughly. So you know something about the right-hand side, like that this is maybe a Lipschitz continuous function, which is maybe increasing with respect to one variable, something like that, but not the exact formula, or even not at all, no idea at all. And the standard approach nowadays is interpolate the data we have from the sample dynamical system by a regular function, and then instead investigate the associated classical dynamical system given by this function, because after interpolation, you already have a complete formula and you can do all this numerics and so on. But one thing here is a little bit strange, because going back to this picture we had a moment ago, now imagine we have this data sample from a dynamical system, and what do? You build via this interpolation, you build a classical dynamical system, and then most likely you discretize it again, and then you use these topological tools to get to the conclusion. And clearly, start in the world of discrete mathematics, a finite set of a finite piece of time series or a cloud of vectors. Then you build something which is in classical continuous mathematics, because here the tools are very well developed. And then you discretize again to something completely different. You discretize just to use the tool to get the conclusions. So the question is it possible to do a combinatorial models where we could use directly these topological features without the need of constructing discontinuous model. So it would go like this, a kind of combinatorial dynamical system, but not just a directed graph, something more so that you could have at least hope for adapting these topological tools. So you could define this topological invariance for this combinatorial dynamical system the same way as we do in the classical case and draw the conclusions directly. So I already mentioned the two flavors of the sample dynamical system. Finite cloud of points and map acting on these points, or a cloud of vectors. And today I concentrate on the cloud of vectors, although you can do similar things. It's slightly more complicated also in this case on the left-hand side. So first of all, if we want to speak about topology and we only have a cloud of points and for cloud of vectors, we need to get this topology from somewhere. And people in topological data analysis who work in this subject for more than 20 years now. In particular, Pavel is a local expert in this area, how to do this. So in principle, without going into details, there is a huge literature on this subject nowadays. You have so you just start with a cloud of points, and then you have two options. Either you so these points most likely are just vectors in some high-dimensional vector space. So you still take a division to, for instance, cubes, high-dimensional cubes, and then you look where these points of clouds sit, and you took this part of this space where you have at least one representative, or maybe at least two representatives, or you just try to build a symmetry complex out of this. And so the techniques, the most used techniques are Vitoris complex, Czech complex, other similar complexes, and so on. What is interesting here, once you build, it doesn't matter whether this will be this cubical set or the single complex or more sophisticated cellular complex, you have, of course, the topology inherited from the Rn, this high-dimensional vector space. But there is an alternative which is interesting, namely, in a cellular complex, you have this concept of phase. Once you have a complex of phase, this gives you a partial order among phases. Phase of a phase is a phase. So you have a partial order. And once you have a partial order on the finite set, the Alexandrov theorem says that actually you also have topology. And these two topologies seem to be very, very different. At least they are not homeomorphic for obvious reason. One is on a finite set, one is on a continuum. But nevertheless, in terms of algebraic invariance, in terms of algebraic topology, there is a McCord theorem which says that actually this is they are equivalent. Again, I do not go into details because you mostly are safe using the topology inherited from Rn. And the only reason I mentioned this Alexandrov topology is that I'll start introducing this combinatorial topological dynamics in a moment, and certain definitions will be very analogous to classical ones, but some features will be very different. And that is actually a kind of obstacle that you see something suddenly is very different, and you do not want to adjust it to be like in the classical case, and it's wrong. And this is wrong because actually the right topology is the Alexandrov topology. And when you look at things via the glasses of Alexandrov topology, that what seems to be strange is actually very natural and understandable. Okay, so let's go back to our clouds of vectors. And I skip the way we reconstruct the space. So we have a symmetry complex, and we want now to give it a kind of combinatorial dynamical system. Text. How to do it? So how to set up a combinatorial model of dynamics in this setting? So we need a directed graph. And a hint how to do it goes to another American mathematician, Robin Foreman, who at the very end of the 20th century proposed a purely combinatorial version of Morse theory. Instead of taking a manifold and real valued function on the manifold which generates a gradient dynamical system and so on, like the classical Morse theory, he just took a simplicial complex, defined an analog of Morse function. I will not introduce it here because I have no time to go too much in his version of Morse theory, but in particular, he defined what he called a combinatorial vector field. And I have to admit that in Pavel, what year was it? 2005, 6, something like that. Just a few years after the publication, Pavel was at the time student in Krakow.
Master student.
Yes, he came to me with this paper and he showed it to me and he said, it sounds interesting. And I had a look and I completely misunderstood that paper. I said to Pavel, no, you are wrong. This is something strange. I have no idea what this guy is talking about. It took me years to understand that it's actually very interesting, valuable. The problem is that, yes, you see the definition the first time, it sounds completely not to be related to dynamics at all. So what is this definition? There are still various flavors, equivalent ways of the people presented. The shortest and simplest definition is that a combinatorial vector field on a simplicial complex, actually on the collection of cells of this simplicial complex, it may be actually also a CW complex. It's a partition of this collection into sets of cardinality at most two, so singletons or doubletons. No condition on singletons, one condition on doubleton, that if you take a doublet, if you put them into a doubleton, then one should be a face of the other of the dimension 1. And then since one dimension is higher than the other, this gives you a sense of direction. By convention, you go from the lower to the higher dimension. So in this example, this is a doubleton. This edge is paired with this triangle. This is a singleton. So you have a couple of singletons, a couple of doubletons, and this is his idea of a combinatorial vector field. Yeah, I already mentioned that we expect a directed graph. This is formally a directed graph, but it does not give you much chance of solutions because we expect that the solution should be a walking directed graph. No way to use an interesting walk if you have just you have a partition. So if you are at the end of an arrow, because you draw naturally arrows, you cannot be at the start of another arrow because that vertex will belong to two depletons and in the partition. But actually, there is also already in Forman's paper visible this concept of solution. Although when you look into his paper, he was not so much dynamically oriented. He just wanted to do Morse theory. Dynamics was just a part of Morse theory, but not the dynamics itself was of his interest. So this is his concept of path there, and he just says that when you are at the end of an arrow, you can actually go anywhere to the boundary except this part of the boundary he came from. So I call this now explicit arrows, which are given when you want to define a combinatorial vector field. And this implicit arrow, which are marked here on the right by this blue broken arrows. And then you have a direct graph and really a chance to travel many different ways through this graph. In particular, you have a periodic solution here because you go along explicit arrow up, and then you go down to the boundary, up again, and so on, and then travel around. This dynamic is multivariate. I already mentioned that. So if you feel you are both rotating here, so from minus infinity, you can keep rotating. And after half of time has passed, you decide now you are bored and I want to go somewhere else. So for instance, you can go you can take a distraction to this singleton, and the singleton is treated as a stationary solution. So you can stay here forever. Okay, so we have this analog. Actually, you can put a slightly even more than a general definition. A combinatorial dynamical system is a directed graph with vertices in the set of cells of the cellular complex. Actually, you can just take a finite topological space. This is more general than this case, because here I do not go into the question where this directed graph came from. And actually, with this approach, you can have something which is not with continuous time. Whereas the spirit of this combinatorial vector fields is that although everything is finite, the hidden time here corresponds to the continuous time somehow. Okay, and you can define a solution as a walk to the graph. It's convenient to have sometimes a finite walk, then I speak about the path. So this is the concept Forman used. A big infinite walk will be referred to as a full solution. And then you say that the set of cells is invariant if for every cell in this set, there is a full solution sitting in this set. So you have just a walk in this directed graph, but you stay in this subset of cells. Okay, I need one modification in the Forman idea. Again, he was just oriented to Morse theory. He needed just a tool. But if you try to use it for dynamical systems, you will quickly run into trouble. Because imagine here, I divided my space. For simplicity, I assume that I really understand my flow. But nevertheless, I try to imagine what may happen with my discretization. At every edge, there is, at least in this example, there is a unique direction. So you know into which complementary cell you enter. So then this might give you a hint how to do this Forman theory. And here this is clear. This edge should be associated with this square to make this Forman vector. But here you are in trouble because you want to associate this edge, and also this edge with this square, and you have no longer partition. So a modification of this idea is needed. And actually, a combinatorial multivector field on the finite topological space, so on a collection of cells of a cellular complex, is a partition, but not just into singletons and doubletons. You allow any locally closed set. Locally closed set is something which is not so easy. This concept is not so easy to be found in a textbook on topology. You can find it in Engelfin's general topology, this concept. The Alexandrov theorem lets you translate actually all these concepts in finite topology into posets and vice versa. So what corresponds to locally close in the language of posets is that you have a poset convex set. A poset convex set is just a set with the feature that if two elements are in the set, then everything in between in terms of the poset is also in the set. So when you divide into locally closed set, you can still get this dynamics. You get a combinatorial dynamical system in the form of a multivariate map, which just tells you when you are at the vertex, what can be your next step. The formula is that you can go actually anywhere to the closure or anywhere with either multivector. The interpretation is that multivector is treated as a kind of black box. So this is something where I have not enough information what's going inside. So I just do not want to exclude any option, so I allow any movement inside the multivector. But if I want to go from one multivector to the other, I have to, and here comes again this feeling of continuous time. I cannot jump arbitrarily to a different place. I have to cross the boundary. So I have to go first to the closure, and the closure may be this part of the closure may be in the different multivectors, and this way I can continue. And it turns out, so here is an example of a partition of a cellular complex into multivectors. Most of them are vectors, but not so. Here is a multivector. This is convex because I have here this vertex, this 2D cell, but also these two edges, because since I already have this and this, the energy in between in terms of the base poset map is also there. Here is again an example of a 3D trajectory. I do not draw these implicit arrows because the picture gets quickly incomprehensible. But you know that you can always go to the boundary. It's not drawn, but you can always continue to the boundary. And you can introduce, I skipped here, sorry. Yes, I skipped this definition, so let me go back to it now. Once I have this combinatorial dynamical system as a directed graph with vertex set a finite topological space, I can define an isolated analog on an isolated invariant set. It's just an invariant set which admits an isolating neighborhood, and by that I mean a set n, sorry, not will it work? It just it's being closed. Not so it's so maybe. This should have been. This slide. Okay. Now this is no longer working. Okay, probably it's not worth to lose time for that. So maybe you could go to that. Okay, so just here with this definition, an isolating neighborhood has a closed set and containing S such that every path which is in N, but its endpoints are in S, and actually the only way to get it is that the whole path is in S. When you think a little bit about it, it's close to the concept of excluding internal tangents, because a path which starts in S, goes away to N, and then comes back to S would behave in some sense like an internal tangency. So there is here this analog of the isolated neighborhood. And then the Conley index may be defined in the setting of this multivector fields as the homology of the closure of S and this closure of S minus S, which I call matrix. I have found no name in the literature, at least not broadly accepted name for this simple topological concept, just a part of the boundary which does not belong to the set itself. Because actually you can prove, I did not show this theorem here, but a set of cells is an isolated invariant set, if and only if it's locally closed in itself, so convex itself in the sense of poset, and it's also B-compatible. Skip the other part. What matters here is that actually you can prove that this mouth is always closed for the isolated invariant set, and it plays. It's like the analog of the exit set in the Rajewski theorem.
Is it even only if?
It's even only if, but with the D-compatibility.
Okay.
Okay, so we have Conley index. I did not mention Mrozek composition, but this is the extension of Morse theory to the setting of general, not necessarily gradient dynamical system in Conley theory. So roughly speaking, you have an isolated invariant set, and then the collection of subsets indexed by a poset, a completely different poset, not related to the posets I already mentioned, with the feature that at any point, so I'm back in the classical setting for a moment, recalling the classical concept, that if a point is in your isolated invariant set, but not in one of these subsets, it actually is on a trajectory such that when you go backwards along this trajectory, you limit in one of these subsets, forwards also in one of these subsets, and these two are uniquely determined, and moreover, this backwards is above this downwards, this forwards when you look into this indexing. So based on this definition, you can build, for instance, the Morse inequalities analog to the classical Morse theory. And so here is an example in classical case, very simple example. So the invariant set is just this disk and everything inside. This is our S. The Morse decomposition consists of the periodic trajectory here and 3 stationary points. This is so-called Conley-Morse graph with the Conley indices as labels. And you can do the same in this combinatorial setting. So you can introduce this definition, which looks more or less the same. You can build a Morse Conley graph. You can prove the Morse inequalities. So the whole theory carries over. I still have it.
I think 10 minutes.
Okay, so maybe let me make this comment. Here in this example, again, this periodic trajectory. This is an isolated invariant set. When you look at it, just use the topology created from the plane. So you should consider this as a collection of cells, and the cells which go into this isolated invariant set are these 3 2D cells and 3 edges, but not the boundary and not this fixed point inside. This is not a closed set in neither in this Alexandrov topology nor in the topology inherited from Rn, but still an isolated invariant set. In the classical theory, you prove that an isolated invariant set is always compact, and since it's compact, it's closed. So this looks strange, and this was actually an obstacle for many years for us to understand what's going on. And the way we explain it right now is that the right topology is the Alexandrov topology. Alexandrov topology, with the exception of the discrete topology, is not Hausdorff. And feature you are familiar with, the compact set is closed, is true for Hausdorff spaces. If a sparse is not Hausdorff, then you cannot conclude that something is closed. And finite topological spaces are clearly compact trivially. Some people even just assume Hausdorff, define the compactness only for Hausdorff spaces, because this is where it really gives you what you want. But formally, you can say, okay, a finite space is trivially compact, but compactness does not imply closedness. And this is the explanation that we have to accept that isolated invariant sets are no longer closed in this segment, but otherwise what's important carries over. There is a question how to construct a combinatorial multivector field from cloud of vectors. And also, are there any formal ties between the combinatorial topological dynamics and classical topological dynamics? So the answer to the first question very briefly is that, so this thin arrow, I assume that I have a cloud of vectors, as I've already shown, and I want to construct also a combinatorial multivector field. So I reconstructed my space. For instance, this is a synthetized complex. And then I have this thin arrow is my arrow. So the vertices of the simplex complex are these points in my cloud of points. And at every point, I have this vector from this cloud. But such a vector will probably point inside one of my triangles. And then, okay, so I would say, since then I want to have this vertex and this triangle, one multivector, but then also this edge and this edge. But sometimes it's not the best choice. Sometimes when this vector is close enough to one of the edges, you may say, no, in this case, I want to associate this vector with this edge only. This raises question, actually, you pick up a threshold of the angle. How far are you from lower dimensional faces to make the decision what choice to make? And actually, topological data analysis is already helpful to make right choices. About the other question, flow reconstruction, it took us like 10 years to find the proof. What we believe from the very beginning must be true. So here is a very simple example of a Forman vector field. So actually I have even only have singletons and dubletons on this very simple circular complex. Maybe let me go here first to this right-hand side. So we immediately knew how to draw a classical flow, which would have the same Morse decomposition as the combinatorial one, the same Conway Morse graph, the same Conway indices. But to prove it that it's always possible, it turned out to be technically very, very complicated. Actually, this auxiliary cellular division, which is presented here in the middle, was necessary. And still, even with that, it was quite technically complicated to come up with this theorem, which I managed to prove with Thomas Banner 2 years ago, eventually. Given a Morse decomposition of the combinatorial vector field of a single complex, there is a semi-flow on the geometric realization. So now I just forget about the cells. I treat it as a subset of Rn of the complex with the same Conway Morse graph. So this means that there is always a representative, at least one, which behaves the classical flow, which behaves like our combinatorial flow. This kind of theorem is important because if you build these combinatorial dynamical systems out of the data, then the question is, how does it relate to reality? Because we still believe there is a classical dynamical system there. We cannot grasp it somehow. So at least you know that what you can understand via topological features actually applies to at least one of semi-flow. And very brief, so this is borrowed by Robert's permission, a picture from this paper in Bulletin of the American Mathematical Society, where it quickly explains one of the main tools of topological data analysis, namely persistence and combinatorial persistent homology. And the title is too early. I want to explain it that it's with this combinatorial dynamics, it's very easy to use these tools in various settings. I already mentioned one, the choice of this threshold, but there are some more. So roughly the idea of this persistent homology is that you keep building gradually your initial complex by adding cells. And then certain homology generators, so holes in the space, may appear, and like here there is no one cell, but there is already one here. But later, when you keep adding, it may disappear. So you can measure the time between the birth of the hole and the depth of the hole, which gives you the so-called barcode. And actually, the rough idea is that the short bars in this barcode are most likely related to just inaccuracies in the data or some noise, whereas long bars probably represent the real topological feature of what we try to understand. So actually, you can use this. So here is an example based on Hopf bifurcation, where you can use it just from multivector fields. But since I want to explain it in a situation where you really know what's going on, so I take a dynamical system on the plane with a parameter undergoing Hopf bifurcation. So you have just here a cloud of vectors. So I just pick up a point and take the vector from this analytically known vector field. So in Hopf bifurcation, you have a repetitive fixed point, and then a periodic trajectory is born, and it keeps growing. There is still a fixed point inside, which is now repelling, which is now attracting, the periodic trajectory is repelling. But you see it only by a count of points. And you could imagine that it was not just from a formula, but just from sampling, from experiments. You just got a cloud of vectors. So the question is what you can see when you try to understand what's going on via topological tools like the Conway index. So first of all, you build your combinatorial multivector fields. So here is an application. So now this is no longer a cloud of vectors, but it's a multi-vector field built out of this cloud of vectors. This is the magnification of the piece. And there is a small, for this multi-vector field, I look for invariant sets. So there is a small blue invariant set here, which corresponds to everything which is bounded in this square. And then when you modify the parameter, it keeps growing. But after some time, it is longer fits into the square when you make the studies, and the maximal invariant set here is now only the fixed point because the period trajectory already went out of the square. And this is actually the exit set now, the red one for this isolated invariant set which was born here. So you can actually do the TDA here, and you actually grasp the presence of this Hopf bifurcation via this barcode, where this red bar corresponds to this attracting bounded region, and then the blue one corresponds to this periodic trajectory, which is I probably mixed them over. Yes, the H2 homology. So this is a repelling fixed point here. You no longer see here the periodic trajectory. The maximal invariant set is just the fixed point, but it's repelling, so its homology is H2. Of course, this is just the summary, but we did this computation via several stages. So these are just 3 examples, but I think in the actual computation there was like 100 stages, and you could see where the bar code changes, and this way you can grasp dynamical features. And I'm probably out of time, so very, very briefly, very recent results. You can, so this is picture taken again from the old Williams paper explaining the geometric model of what is going on in the Lorentz attractor. And you can build a combinatorial model of such a Lorentz attractor. And moreover, what we managed to prove recently with Robert Szednicki, Thomas Walker, and his student Justin Ford is that when you spot, so you imagine you have again a combinatorial multi-vector field, and you manage to find an isolated invariant set like this. If you assume that the actual flow, one of such flows we are able to construct via a theorem I mentioned, is transversal to every basis of codimension 1. And actually, this semi-flow must be chaotic in the sense of infinite number of periodic orbits. This opens a way, so this is a 3D analog of the situation, a combinatorial dynamical system. What we conjecture is that for the Lorentz attractor, if you do the same that you just try to get a cloud of vectors out of this, and you build a combinatorial multi-vector field, you should be able to find such an isolated invariant set which satisfies these assumptions. That would give another computer-assisted proof of the existence of chaos in the Lorentz attractor. Okay, and maybe I will no longer speak about more spread decompositions, but just concluding remarks. So you take data sample from the dynamical system, you construct a combinatorial dynamical system, and out of that you get this finite concise descriptors, Conway indices, Conway Morse graphs, connection matrices, which I have no chance to touch here, but it's also possible to do this in another setting. And out of it you can get this. So now, assuming that your real dynamical system is transversal to what you constructed from the data, you can use all these theorems developed earlier for classical dynamical system to draw the conclusions. So this is a kind of two-sided bridge between finitely continuous mathematics, a direct bridge. Instead of going first to continuous model and then discretize again and so on. The resulting correspondence covers gradient and recurrent dynamics. It provides concise global descriptors. They may be studied by means of topological persistence. And the last, but definitely not least, the probabilistic methods may be introduced into combinatorial dynamical system. This, I'm not a probability man. I always admire it. I think you need a special kind of brain, special mind to do properly stochastic dynamical systems. But my collaborator and our common student, so Bogdan Batko, and our common student, Damian Sadowski, actually treat these clouds of vectors as Gaussian processes, and then you can construct algorithms which not only can give you a multi-vector field, but you can request first a level of probability that the real system may be represented as this, by this combinatorial dynamical system, and then everything what you get with the same probability may be applied to it. So here are some references. Thanks a lot for your attention. And sorry, I took probably all my time.
To jest jakieś krótkie pytanie, mam za wiele czasu, ale...
Okay, I'll go for English.
So you're already able to your last results on transfer personality with this. I'm wondering if you could have some sort of theorem like that. You can have a nice dynamical system, nice to behave without any fractal structure in dynamics. Can you say that there exists a sort of composition of a certain granularity, so a certain maximum granularity, on which you see exactly everything that can be seen in this system?
Yes, so this is actually, in the conclusion I said two-sided bridge, but actually I explained only one side, so via this theorem, from the combinatorial case to the classical case. The other direction is of course more complicated because you assume certain resolution and you cannot see beyond this resolution. But yes, when you assume this resolution, actually there are ways of constructing this cellular decomposition, which is transversal, and then you pick up exactly what you can see up to this resolution. This is a challenging problem because it's not so easy to construct this cellular decomposition with transversality. But there is now in our group a lot of research because it's an old subject. Konstantin tried to use it for all this theory with his actually first PhD student, and they found it quickly that it's difficult. But at that time, they had no motivation to do it. We have no motivation to do it, and there are ways to achieve it. Maybe not perfect yet, but in terms of algorithms. But yes, thank you.
Okay, let's thank our speaker once again.